Hello, this is Bruce, and I think we have come to the end of our series on calibrating analog inputs. And in this case, we're going to use the Theramin code we've been developing, and instead of number version 6A, which calibrated continuously inside loop and had problems, for example, it didn't shut off if the room went dark for a moment, we can instead calibrate in setup, try to control the start and stop time of calibration, and prevent this problem from happening. So we're going to try some new tricks in this piece of code. And one of these is to do what's called real-time programming, in which we watch the system clock to know how long we've been calibrating for, which will be 5 seconds. And to do that, we're going to use a new kind of variable called an unsigned long. The Arduino has a clock that ticks in milliseconds, thousandths of a second, and can get up to about 4 billion in some milliseconds before it fills up. This is a lot, and I think comes to about 50 days. The reason why it's unsigned is half of a computer number is usually, or half of the memory for a computer number is usually assigned for the positive half and half for the negative half. If it's unsigned, all of it can go to the positive half. Instead of getting 2 billion plus or minus, we get 4 billion plus. All right, we're going to use the same min-max method that we used in method number 1, 6a, but this time we're going to make sure that it's not too short or too long, and we're also going to wait for a hand to start moving up and down. And 2, we'll start with a simple loop that waits for the light values to start changing, and that's how it's going to detect hand motion. Then we're going to run a short calibration loop and setup. This will be similar to the one that we used in loop, the difference being that it will stop after 5 seconds because it's watching the system clock. And this gives you a lot more control over the light and dark durations. It's much simpler than trying to do it by timing out delays. And finally, some feedback. It will beep 3 times when it's done. And as I point out, you could add indicator LEDs and the like, but this seemed adequate to me. Let's see, we will be using real-time techniques watching the clock. We covered that with unsigned longs. And one special thing about an unsigned long, this is going to be a point 1, 2, 3, 4 under number 4 here. C sometimes does weird things when it converts numbers of one size and sign and type to another size. So it's best to tell it what you want it to do. And if you type in a number that you want to be an unsigned long, which is a slightly strange kind of a declaration, add a UL after it so that C knows not to interpret it conceivably as a negative number if it's got a bit set in the wrong spot. 5. We're also going to use a new looping command called while. And this is while a test is true, you repeat all this code. And you'll see that we're going to make very simple use of this. So I'm going to talk you through all the changes. They're at the bottom of this file. They're mostly there for my benefit. You can also see them on the bottom of the screen to make sure that I play through this correctly. Okay, number 1. We're going to check our version comments. I think I've already updated this. No, I haven't. So over here on the right, Bruce Hubbard version 1.5.1, copy. And I'm going to say continuous auto calibration in loop because number 2 is going to be version 5.1.2, alternative version. Really, this is a fork. This is not, which means the code splits into 2 parallel paths. But I'm going to do it simply as another revision because I didn't like the continuous calibration and loop revision very much anyway. All right, so continuous auto calibration in, that's not setup, in setup. And it's not continuous, but it is timed or controlled perhaps. Okay, let's look through the code and spruce it up. So one of the things we're going to do is we're going to look for declarations that we can turn into constants. These are both safer to use, and they will also speed up our code conceivably, which is going to be running also in real time, sampling the light and trying to produce a reasonable sounding tone. And the fewer memory accesses and etc. that we have to do, the faster it's going to run. So data min and data max are the way they were before for global declarations here. Min is starting at 1023 because it's going to drop, max at 0 because it's going to rise. Frequency minimum, I'm going to set this up to 500. I was trying to avoid the annoying whine before, and the frequency maximum to 2000. And I'm going to make those constant integers because they are not going to change during the life of this program at least. And what else do we have here? We have the time that minimum time that we're having it play the note. That's also a constant. Constant integer note time. I've been experimenting around and I've decided that I like 8 milliseconds. And finally, we have the tolerance. That's the little dead band, dead gap, that prevents it from running at full brightness and full darkness, which keeps it from sitting there and annoying everybody. That number is not going to change while the program executes, so that's a constant integer. Okay, global declarations. Again, these aren't going to change. Constant integer. For the Theramin pin, constant integer for the speaker pin. Okay, we get down to setup, and we're going to take things out of setup that we don't need. We are through looking at our data for the time being, so I almost took out serial begin, but I'll leave it in there just to make it convenient for someone else. Turns out that if you're using tone to run a pin, you don't need to declare it as an output. So I'm going to take away pin mode speaker output. I'm also going to take out the gratuitous put setup in here and run your code once. Well, we're good to go for additional code to calibrate, but let's keep going down our program. So we're sprucing. We're down to loop. Read the photoresistor, data, Theramin pin. So far, so good. Here is the if data, the two statements that we used to auto-calibrate last time. We'll just chop those out, both of those. And we will delete a little bit of empty space here, make things look better. Okay, we read the data from the Theramin pin. We constrain it between minimum and maximum, which we've already calibrated somewhere else. And then if the data is between the maximum minus a little deadband and it's above the minimum plus a little bit of deadband, we're going to map the data between, again, that actual range that we're using to our predetermined frequency min and frequency maximum. We're going to get a frequency out of this. We're going to play the tone through the speaker pin. We're going to delay a little bit, which seems to make tone happier. And if that wasn't true, else, meaning the data was not in the valid range, we're going to call no tone and shut the speaker off until the data returns. Okay, I'm going to make a couple changes down here while we're here. I'm going to take data, who we are declaring to be an integer every time we go through loop. Then we're throwing it away. Then we're making it again. And I'm going to declare it at the top of the program. Same thing with frequency, down here by if data. We declare it and throw it away every time it goes through the if. So we will declare data and frequency at the top of our program, minimize the amount of extra work that we have to do. We'll come back here again. So let's go up to the top. Let's look at our global declarations here. We've got the Theramin pin and the speaker pin. I'm going to look through my crib notes over here, and we're going to add after the speaker pin 4 declarations. And because I can steal them from over here and I don't want to talk for too long, I'm going to steal them and paste them in. And you can pause and type as you would like to. And this will keep the talk a little shorter. But I will tell you what I've done. We're doing this calculation over and over again, right? We're calculating our data maximum plus the band, data minimum plus the band. And I've already mentioned the frequency and the data. We're doing a lot of work, doesn't change. Look down here. If data is less than data max minus tolerance, we're doing that piece of math. It gives you the same value every time you run it, and same thing with data min. So I'm going to take those out of here, and that was a min threshold. This one using data max, I'm going to call the max threshold. Comment that out. V, change min to max. Okay, and we're using exactly the same set of numbers down here, except in the opposite order. Here is the data max minus the tolerance, and I'm going to put in the pre-calculated value there, and I'm now going to look very carefully and try not to make a mistake. If data is less than the maximum threshold and greater than the minimum threshold, map it from the minimum threshold value over here. Double click didn't do it. Map our data from the minimum range through the maximum range to the minimum frequency through the maximum frequency. Store that in our predefined frequency variable and call tone. So we're going to do these calculations somewhere else. Code looks a little cleaner, and we're saving some work that we do repetitive to no benefit. Okay, so we've created a min and a max threshold, a frequency in the data. We haven't given them values yet because we don't know what they're going to be until later. We won't know what frequency is till we run the map command. We won't know what data is until we've done an analog read. And min and max threshold, we won't know until we've completed the setup. All right, so we're in setup and we're ready to go. So I'm going to go over here and look through my cribs. Give me a minute to do some copying. We're going to go to setup. We've taken out all of the unnecessary pin modes. We're going to leave serial begin because someone might want to use it again at some point. And we're going to add the first of our new declarations. And as I say, I'm going to copy these from program I've tested, put them in and tell you what I'm doing. We're going to collect two sequential data values and compare them. How do we know when the hand is moving? Well, we get two different readings from the photoresistor. So these are going to be called data 1 and data 2. They're not constant because they're going to be updated continuously. But what I will do is I will fill the first one with an analog read. Just take a sample of whatever's going on there. I'll take the second one, arbitrarily fill it with the first one. And then how do I know they've changed? I'm going to create a third variable, data difference, and I'm going to subtract data 1 from data 2. I'm interested in when they get to be, that difference gets to be not 0. That's when things get interesting. So how do we know when they get to be not 0? We will highlight and type in the following piece of code, which I have copied from my little crib. And so after we wait for hand motion, and really these are going to be the definitions, the variables. Wait for hand motion dash variables. Because then we're going to do the actual waiting. I'm going to paste this in, and I'm going to say the hand motion wait loop. And I'm going to go up here over to tools. I'm going to say auto format to get my indenting correct. I'll scroll back to where I am. And I've got 1, 2, 3, 4, 5, 6 or so lines of code that I've just pasted in. What's it doing? First, it's using the new command I told you about, the while. While, perform a test, and that test is true. Do everything inside of the loop, and if that test never changes, you'll be stuck there forever. So usually that's a test that gets changed by something that happens in the while loop. Why is tolerance important? That's the jitter that we expect in the numbers based on our earlier observations, just from watching them bounce up and down because of random noise. But remember up here, I subtracted data 1 from data 2. One of those is going to be bigger and one of those is going to be smaller depending upon which way your hand moved and so you don't know which way, and you don't know if it'll be positive or negative. So down here, I'm taking what's called the absolute value, ABS, open parentheses, of the data difference. That means make it positive regardless, and ask if it is less than the tolerance. If it is, we're going to declare that nothing has moved. Okay, so what do? Inside, we're going to keep track. We're going to take our first reading, which was our real reading. We're going to move it over to data 2. Now data 1 is free to do something with. Well, we're going to just hang out for a tenth of a second. I said we wouldn't do that earlier, but here we're sort of waiting for somebody to get ready to start using the machine. We don't need to be too speedy. Eventually, we're going to call analog read again on the Theramin pin. We're going to put a new value in data 1, the old values in data 2, and we're going to recalculate data difference. It's data 1 minus data 2. End of the while loop, which means it goes, there's the matching bracket, goes back up to the top, takes the positive data difference and compares it to the tolerance. Is it less? Then it continues to go around in this loop, each time storing the new data into the old data, waiting a bit, reading the Theramin pin again, calculating the difference, and waiting for it to change. At some point you'll move your hand, and this will be greater than the tolerance. The while loop will end, and we can now move on to real calibration. Okay, so we'll go over on the left here, and again we're going to copy some pre-written code, keep things moving along here, paste it in over on the right, and this says these are our auto-calibration timing variables. Remember I said those need to be unsigned longs because times are going to be these huge positive numbers, and where do we get our starting time? We're going to compare, we're going to start and we're going to end. So the starting time is whatever the millisecond clock currently is. And you get that by calling the function millis. And every time you call it, it'll be a little bit bigger than it used to be. It doesn't mean anything in any absolute value unless you started a stopwatch the moment you powered up or reset your Arduino. And so usually you use differences. You read the clock, you wait a while, you read it again, and then you subtract those two and see how much time has gone by. So the start time is the current reading of millis. The end time, unsigned long, is interesting. That is whatever the starting time is plus 5,000 UL. Remember, these are milliseconds. So start time plus 5,000 milliseconds, unsigned long, and that means 5 seconds later is our end time. That's how we're going to determine when our calibration is done. So we're going to copy a little bit more code from my crib over here on the left, and I'm going to paste it in under my time definitions. And this is called the auto calibration loop. You can pause the video and type these things in, or you can grab them off the end of the text file. While again. This while is continuously testing the millisecond clock. It's asking, is it true that it is less than the end time? All right, that means that we should be doing something until we get to the end time, which is 5 milliseconds after the start time. Okay, so that's our test. It's going to be true until 5,000 milliseconds go by, and then it will be false. What's it going to do? It creates a little local variable data, and it calls analog read on the Theramin pin. It calls tone speaker pin on the data. Doesn't matter what the data is, it's going to be kind of low frequency, but it gives us a audible feedback without doing too much work. And then we have our familiar calibration. If the value of data is greater than the current data max, move it to data max equals data, make data max bigger. And if the current value of data is less than current value of data min, stick it in data min and make it smaller. And then wait a little while. You don't want these loops to run too fast. I was playing around. There is another delay function called delay microseconds, millionths of a second instead of milliseconds. And I kind of like 9530, around 9.5 milliseconds. As a delay, it ran this loop at about a rate of 10 milliseconds or so, and That appealed to me. This is going to run for 5 seconds. We're going to be updating data min and data max. Then millis will get to be a little bit bigger than the end time, and we'll be done. So what do we do when we get done? Well, I said earlier, scroll this up a little bit so that you can see what we've been talking about. First, we're going to check our version, blah, blah, blah. We're going to clean up setup and remove unnecessary code. We ran the short loop, waiting for hand motion. We ran the real calibration loop for 5 seconds. Now we're ready to toot 5 times. And you can see the code that does this has also been copied to the end of your document. I'm going to go get it, off my version C of the code that I've been testing so that it doesn't make mistakes. And I'm going to paste it in over on the right here on our growing auto calibration program. Okay, the calibration loop has finished. You've been moving your hand up and down, hopefully. It doesn't check how much. I had code that tried to do that, and it just made life really complicated. So we just assume that you're a good citizen of the world here. You've moved your hand up and down and calibrated it. And at the end of this, we turn off the speaker, which has been running your hand motion. We wait for a brief silence. Then for I equals 0, while I is less than 3, I plus plus, a little for loop. We are going to play the speaker at 5,000 hertz. It's a little squeak, delay a tenth, and turn off the speaker. So 3 times we're going to go beep, off, beep, off, beep, off. So you'll hear that as 3 little toots, and that will tell you no more auto calibrating, you're ready to go. All right, 6B, I'm going to save this at this point in case we have a tragedy. All right, now what are we going to do next? We're going to go down to our main loop. We declared data up as a global, so we don't need to declare it here. Analog read. We declared constrain, data min and data max. We've got max threshold and min threshold. Let's go back up and see if we sort of overlooked those guys. Yeah, we never calculated those. Okay, so after we got our data min and our data max, we need to make that calculation. So we're going to go back over and look here for the things that we have forgot to do. So where's a good time to calculate data min, minimum and maximum threshold? Well, anytime after we've done the calibration, we might as well do it next. Set the thresholds. Remember that we identified this calculation, data minimum plus tolerance, data maximum minus tolerance, as being done over and over again, wasting time down there in loop. So we made a min threshold and a max threshold. And we did those calculations up here in setup once. And we'll just toss that in there between the end of calibration and the beginning of the squeaks that say that we're done. So that's good. We've taken care of that. So now we have data. We've got max threshold and min threshold. That's been taken care of. Frequency is populated. It's already been defined. And so I think we only have one more thing to do, and that is to try and speed things up just a little bit more. Loop actually exits and then starts over again. And I don't know if that creates little sonic glitches or not, but let's prevent it from doing that. So I'm going to say while, open parentheses true, close parentheses, open curly brace. Do everything inside loop down to the very bottom and close the curly brace that belongs to while. Now, our whole musical world is trapped, while true, forever, inside a little loop here where I know exactly what's going on, whereas I sort of don't know what happens after loop ends and before it starts again. So when you're timing things, that's sort of important. Make sure that you keep track of everything that you can. Auto format. Get the indenting right. Okay, so loop, indent to while, indent to data. Everything in here should be good. We should have reviewed it earlier. I will do a test compile, make sure that I haven't forgotten anything. All right, that looks good. One more time, while true, read the Theramin pin. constrain it between the minimum and the maximum that we auto-calibrated up above. While the data is less than now the pre-calculated maximum threshold and greater than the pre-calculated minimum threshold, do a map of data between that minimum and maximum to a pre-selected frequency minimum and frequency maximum. And I've just picked those to be low enough that they're not too annoying. Tone, speaker pin frequency, it will run till it gets a new frequency, and this loop actually takes something like 8 milliseconds to run as configured. So the timing in here, so this is a little bit interesting. Timing of the loop below is about the delay of note time, our explicit delay that we've put in to make sure that frequency min runs for enough time for it to really get fired up, plus 0.31 milliseconds. All right, so I did some timing testing before, and it looks like this thing, when it is not producing a tone, it's running for about 1/10 of a millisecond. When it's producing a tone, it's up to about 3/10 of a millisecond, plus any additional time we've added. So it's a pretty fast loop now. Less, except we've slowed it down with no time. Okay, so that's a good comment, worth sticking in there. How did we get that? So I'm going to go over here to the bottom of the document, make a copy, and go over here and stick in some code which I used to do the timing, and we will come back to that at the end so that you can stop if you are tired of listening to me. Okay, let's back up out of all of that code down there. Let's go over to our main program. Let's look at the loop, which is the one that's going to work. Test compile again. Make sure the Arduino is plugged in and the proper modem is defined. And I'm going to upload it. Compiling the sketch, uploading. Okay, my system is set up under the table lamp. I'm going to go put my hand under it, and you'll hear it start to calibrate. Hand now. Okay, low, high, low, and then let's see the light, full light. Oop, and you hear that little chee-chee-chee-chee? It was done. That was 5 seconds. Okay, so it should now be ready to perform. Take my hand away, and it's through performing. And if I turn off the light, it should not run. I will turn off the light. It's quiet. Turn on the light. It's quiet. Our thresholds are great. We could make it work in a, can't change the frequency by running your hand up and down. There are all kinds of improvements we could ask for. But if I go and push the little reset button on the Arduino, I can bring my hand over here again and move it up and down only by about 3 inches. Okay, so that little thing at the end there. Okay, I'm moving my hand up and down. You can't see, but it's running through the whole range as I move my hand up and down by about 8 inches. Okay, not terribly useful or great. That's the way a small tone correction goes. I will save this, and you can stop at this point. What I will do, however, is go down to the bottom of this, and I will talk about the timing program. I am going to go and copy this out of here, just like this. It's got unsigned long time equals millis. It defines a count. It turns on setup begin. Here's the while loop. We'll get there. Okay, so let me take this, go up to while, and I'm going to just replace that one line, while, with this chunk of code that I've just copied from the bottom of the program. I will call it timing. It still has the while loop in it. We just took out the one we were using and replaced it with a new one that was kind of sandwiched on both sides by code. Okay, so that's what we did. Don't need to go any further down. Go over to Tools, Auto Format, indent things nicely. What did I do? Loop starts, and I declare a new variable. Unsigned long time, take a new reading of the millisecond clock. Define a variable called count. It's equal to 0. Start setup at 9600, and then the while true loop. And everything is the same except we're increasing the counter by 1 each time, and every 1,000 counts, print out how many milliseconds have gone by, is what the comment says. So the question says, if count is equal to 1,000, then serial print line, the current millisecond clock minus whatever time we started it at, we'll print out some milliseconds, reset the count to 0, reset the time to now, and go on down and continue with the music. Okay, so let's go and do a test compile, make sure I haven't made a mistake, and it doesn't like setup down here inside loop. All right, setup, serial. That's why things get tested before you run them. Okay, it's not setup begin, it was in setup, and I moved it to loop. Okay, doesn't matter where you do it. You only need to do it once though. So it's outside the while true. So we do it once because loop never exits. Okay, let's upload this. Done uploading. Let's go over here to the right. Let's open our serial window. There it is over on the left. We'll scoot it over a bit to make it convenient to see. Nothing interesting is happening. I'm going to start calibrating. Go up and down for 5 seconds. Okay, there it was done. Okay, that is the number of milliseconds that 1,000 times through the loop takes. So it's about 0.12 millisecond, okay? If I start making time, and actually the easiest way, see, it gets a little bit bigger. 800 popped by. If I stick a styrofoam cup over my photocell, that turns out to be a good way to get it to kind of run uniformly. Okay, the first one doesn't count because we started halfway through something. Next one ought to run for, 8 seconds and 309 milliseconds. 8.3 milliseconds per loop for 1,000 loops. 8311. So that's how you do timing of how long something takes. And if I go back and I move my hand up and down, I will get all kinds of different timings coming out depending upon how, depending upon how much I let it spend doing almost nothing, not printing out time. It's down to 2.4 seconds and so on. So you got to be a little bit careful where you actually test your seconds from. I am not going to save this last version because it has this extra code added to it. Actually, what I'm going to do is I'm going to take it out, back down to while true, cut. I'm going to restore my while true. I have my little timing that I discovered 0.31 milliseconds, and fix the error down here. That is serial, not setup. Okay, so we'll save this. And quick test to make sure that it's not broken. Okay, I usually take my hand out at the end of the 5 seconds, get a clean. All right, so Theramin is live. That's it, folks. Thank you very much.